Imagine you are in a performance testing interview. You are running a LoadRunner test with 5 load generators. Initially, everything looks normal, but as the load increases, response time starts going up. The application team tells you the application servers look healthy. Then the interviewer asks, how would you determine whether the load generators are responsible? Would you simply check CPU and memory? Not so fast. High CPU doesn't automatically mean the load generators is the bottleneck. We need to investigate the evidence and prove it. So, where do we start? Let's find the point where the performance behavior actually changes. So, the first thing I want to identify is the change point. Suppose we have three important load levels. At 500 virtual users, response time is stable. At 1000 virtual users, response time is still stable. But around 1500 virtual users, response time starts increasing. That 1500 virtual user reason becomes extremely important because now I don't need to investigate everything randomly. I can ask a much more focused question. What changed when the workload reached approximately 1500 virtual users? This is where performance investigation becomes much more effective. I compare the system behavior before the change point with the behavior after the change point. And one of the first thing I want to compare is the behavior of each load generator. Now let's compare the 5 load generators. LG1 is around 55% CPU, LG2 is around 58%, LG3 is around 57%, LG5 is around 56%. But LG4 is sitting around 95% CPU. Immediately, LG4 becomes suspicious. Notice what I'm saying here. I'm saying suspicious. I'm not saying LG4 is definitely the bottleneck. That's an important distinction. The other generators are behaving relatively similar, while LG4 is showing significantly different resource behavior. So my next question is, what exactly is happening on LG4? I want to investigate its CPU behavior in more detail. And then I want to determine whether the other major resources show stronger evidence of a limitation. Let's start with CPU. On Windows, I can use Performance Monitor and monitor percentage processor time. On Linux, I can use tools such as top and vmstat to understand CPU and broader system activity. But I'm not interested in one random CPU spike. Suppose the CPU progression looks something like this: 60%, 74%, 88%, and finally around 95%. Now that's more interesting. Why? Because the CPU pressure is increasing as the workload increases. And if that sustained CPU pressure occurs around the same point where response time begins to degrade, CPU becomes a stronger bottleneck hypothesis. But again, 95% CPU alone does not prove the bottleneck. The correct question is, does the CPU pressure explain the performance behavior we are seeing? To answer that, I need to investigate the major resources. Now let's eliminate competing explanations. First, memory. On Windows, I would examine memory available bytes and supporting paging indicators such as pages per second. On Linux, I use free-h and vmstat. I am looking for the actual evidence of memory pressure. For example, declining available memory together with increasing paging or swap activity would be important evidence. Next, network. On Windows, I can examine network interface bytes total per second and relevant error or drop indicators. On Linux, I can use SAR and IP commands because a load generator is constantly sending requests and receiving responses. Finally, disk and I/O. On Windows, I can examine physical disk average disk second per transfer and where useful current disk queue length. On Linux, I can use iostat or a more detailed iostat-exit. So the purpose isn't to collect every possible metric. The purpose is to determine whether another resource provides stronger evidence of a limitation. In this scenario, after investigating these resources, we do not see stronger bottleneck evidence than the sustained CPU pressure. So CPU remains our leading hypothesis. But now I want to go one level deeper. High CPU tells me that the processor is under pressure. But I still have another question. Who is actually consuming that CPU? This is where process level investigation becomes important. On Windows, I can use Task Manager or process related performance monitor counters. On Linux, I can use stop or PS commands. Now, suppose the investigation shows that the high CPU consumption is coming primarily from the workload generation related process. That is much stronger evidence. Because now my investigation has progressed from CPU is high to a specific workload generation related process is consuming significant CPU. So the evidence chain is becoming stronger. CPU pressure, process level consumption, load generation activity. But I still need to prove that this resource pressure is actually limiting the workload. And that's where LoadRunner correlation becomes critical. At this point, I take my operating system observations and correlate them with LoadRunner. I want to answer several questions. At what user level did CPU start increasing significantly? When did the transaction rate stop scaling? When did response time start increasing? Did errors increase? And most importantly, did these events happen around the same point in time? There is difference between simply monitoring a server and performing bottleneck analysis. I'm not looking at CPU in isolation. I'm connecting running Vusers with load generator CPU, with transaction rate, with response time, and where relevant errors. When these observations line up around the same workload model, the evidence becomes much more stronger. Now let's look at the actual scenario. At 500 virtual users, the load generator CPU is 55%. Transaction rate is around 200 TPS. Response time is stable. Now, if we increase the workload to 1000 virtual users, CPU increases to around 72%. Transaction rate increases to approximately 390 TPS. Response time is still relatively stable. So far, the load generator is handling the additional workload. Now we reach 1500 virtual users. CPU reaches approximately 95%, but look at the transaction rate. It only increases from approximately 390 TPS to around 395 TPS. The workload has increased significantly, but transaction production has almost stopped scaling. At the same time, response time starts increasing. Now the evidence is much more stronger. We have vusers increasing plus load generator CPU approaching saturation plus transaction rate reaching a plateau plus response time increasing. This is very different from simply saying CPU is 95%, therefore CPU is the bottleneck. The conclusion comes from the correlation. And remember, this is evidence for this scenario. It is not a universal rule that 95% CPU always means a load generator bottleneck. Now let's imagine the interviewer challenges you. How do you know the load generator is actually limiting the test? This is where I would explain my evidence chain. First, sustained CPU pressure. The CPU is not just experiencing a momentary spike, it's heavily utilized as the workload increases. Second, process level evidence. The workload generation related process is responsible for a significant portion of that CPU consumption. Third, transaction rate plateau. The workload increases, but transaction production no longer increases proportionally. Fourth, response time degradation. At approximately the same load level, response time begins increasing. Now, these pieces of evidence point in the same direction. So, I have a strong bottleneck hypothesis. But I still want one final step. I want to validate it. This is the step that takes us from a strong hypothesis toward a defensible conclusion. I want to run a comparable workload again. For example, at 1500 users, suppose the load generator is reaching approximately 95% CPU and transaction rate is 395 TPS. Now I change the load generation capacity. I could redistribute the workload across additional load generator capacity. or I could increase the capacity of the existing load generator environment. The important point is the workload must remain comparable. I don't want to change several unrelated variables and then claim that the load generator was proven as the bottleneck. So I compare before 1500 virtual users, LG CPU is approximately 95%. Transaction rate is approximately 395 TPS. With after 1500 virtual users, low load generator CPU and transaction protection increases or recovers. If the previous limitation disappears or moves when load generator capacity changes, that gives us much more stronger evidence that the load generator was limiting the workload. That's the validation step. So let's answer the interviewer. How did we get here? We started with a response time increase. Then we identified the change point around 1500 virtual users. We compared the load generator and found one clear outliner. We investigated CPU and found sustained CPU pressure. We investigated memory, network, and disk IO for competing evidence. We went one level deeper and identified the workload generation related process consuming the CPU. Then we correlated the operating system evidence with LoadRunner. At 1500 virtual users, CPU increased sharply, transaction rate plateaued, response time increased. And finally, we validated the hypothesis by changing the available load generator capacity under comparable workload conditions. So now I can give the interviewer a defensible answer. The conclusion is not CPU was 95%. The conclusion is based on the complete evidence chain. Load generator CPU is the limiting factor in this scenario. And that's the key lesson. When you are investigating a performance bottleneck, don't just collect metrics. Build the evidence, suspect, correlate, investigate, validate, and then conclude. That's how an experienced performance tester answers a bottleneck question in an interview. Thanks for watching Performance Testing Mentor. I'll see you in the next video.